Okay, Math 1325, we are going to be doing section 4.3 in a second, but I wanted to point out the one little mistake I made last time, and this is very typical where you make a tiny algebra error, and then when you're all the way through the process, it's hard to go back and find where your mistake was. So I got to, oh, that wasn't it. Okay, so the problem actually started here, number 7. And I applied the quotient rule, and inside the middle of the quotient rule was a product rule. And then when I started to go to town on the multiplying part, this part right here that had 9x, I was doing a FOIL between 9x minus 2 and then this trinomial right here. And I did 9x times 24x squared is 216x cubed. But for some reason then I dropped the x. It should have been 9x times 8x is 72x squared. I didn't have the square right here. And I didn't do it on the last one either. 9x times 24 should have been 216x. So just that leaving off a slight x, that's why my answer was close. I got the front right, but the rest of the terms were wrong because this 72 should have been a square, not x to the first, and this 216 was not a constant. So, and in fact, the 72x squared, if you combine that with 40 minus 48, and then there's also a minus 36 over here. So that should have been negative 12 of those, not negative 84. And then the 216x, that would combine with 16x. And then there's a negative 216x over here. So those two 16x's should cancel. And there would just be the negative 16x. And I had negative 160, why it was wrong. And then the negative 48. The negative 48 would only go with the negative 108. So that would make negative 156. There should have been a negative 156 at the end. Instead of, I added a positive 216 to that. So it caused all three of those terms to be off just ever so slightly, just leaving off an x at one point. And I had it on the first part and somehow miss it on the other two. So that's what can happen sometimes where you make the tiniest of a brain cramp or an algebra mistake of some kind, and it's enough to throw the whole thing off. So last time we did section 4.2 product rule. So today is section 4.3. And this is called the chain rule. The chain rule actually happens all the time. It's just up to this point, it never came into play. But in many problems, while you're doing whatever derivative rule you're doing, the chain rule often just equals 1 for an answer. So then it doesn't really come into play. That's what's happened up to this point. But now it's going to matter on problems. And then as we go forward and learn new rules, it'll always be there hiding in the background. And many students have trouble recognizing it as one issue when you first learn this. And where it comes from is, here's a concept in algebra. When you have multiple functions, we have an f of x, g of x, and an h of x. And we're doing composition of functions, functions inside of functions. H of g of f of 2. So this first question is just a review of algebra. If you remember how to do this, where you have functions inside of functions. When there's a number to start with, f of 2, you do that one first. You only use the 2 on the closest one first, f of 2. And then you would plug that into the f function only. Put a 2 right there. Negative 4 times 2 is negative 8. Minus 1 is negative 9. So f of 2 equals negative 9. So then you take that negative 9 answer, and now you do it on the next one in line. Now you do it on g. Plug negative 9 only into the g function. Negative 9 squared is positive 81. 81 minus 4 is 77. So then you use the 77 finally on the front letter H. H of 77, put a 77 right here. 77 minus 2 is 75. And if you have 3/4, you have 75 cents. So 75 divided by 3 would be 25. You get, sometimes there's only 2 of these. Here there's 3, but whether there's 2 or 3, only the last answer matters. You need the first answer to get to the second. Then if there's only 2, then that would be the answer. But then if there's a third one, you use the second answer to get to the third. Only the third answer matters here. So the whole answer is 25. So that's working with the algebra side of functions inside of functions. But next we're going to do the derivative when there's functions inside of functions. So find the derivative of this function y equals 3x to the fourth minus 4x squared plus 8 to the fourth power. dy over dx, that's telling me to do the derivative. So here's what happened. Let me come over here for a second. Number 2 has y equals 3x to the fourth minus 4x squared and plus 8 to the fourth power. We're looking for the derivative of y with respect to x. But the algebra part of this is, say you had a function f of x, and say f of x was x to the fourth power. And then say there was a separate g of x function that equaled 3x to the fourth minus 4x squared plus 8. And then in algebra, they would have you do f of g of x. That's a very common problem in college algebra to solve for that when they give you 2 functions, f of g of x. And we just did one with a number. If it was f of g of 2, you would only do the 2 into the g function. When it's g of x, you still do the closest one first. It's just that there's nothing to plug in. The first answer is literally whatever they say that function equals. 3x to the fourth minus 4x squared plus 8. So this is like on the first problem when I did f of 2 and got -9. Then I'm plugging -9 into the next one in line. The difference here is you don't have a number like -9, you have a whole function. This whole answer is going to go into the other letter, f. F of this whole stuff. And what happens then is you grab all of this stuff and you come up where f is and you put it right where that x is. This x goes away, just like when you plug a 2 in for it. That x goes away and it gets replaced by all this stuff. So you literally get all this stuff raised to the fourth power like this right here. You literally get this. This is where this was born from. This is the algebra. They give this to algebra students. And that's all they do. They don't do anything, but the algebra students do all this, and this is their answer. Now we're going to take their answer and do a derivative of it because an algebra student doesn't know what a derivative is. So the issue is you have a function inside of a function, though. This may not look like that at first, but it literally came from a function inside of a function. So the way I like to think of this is if say you could back up further back in the room, remember my example last time for the quotient rule that had like a product rule mixed in, that one problem that I slightly messed up. If you back up way far to the back of the room and try to stare at this function inside of a function, say it was kind of blurry and you couldn't tell what was there, you would say, okay, I see some kind of parenthesis, there's something in there, but I can't see what's there, and there's some kind of exponent. And then if I told you, okay, the exponent's a 4, but you still can't see what's inside of that thing. So you'd say, okay, what if I was doing a derivative where I just had something to the fourth power? So I pretend that I can't see the inside of it and just say I have something to the fourth power. That's the power rule. So the derivative of something to the fourth power is you do 4 times the something, and then you decrease the exponent by 1. You're really doing 4 times 1 is 4. You rewrite the base, and then you decrease the exponent by 1. So we're just going to rewrite the base. What's different here is it used to just be an x there. You used to have x to the fourth, and then the derivative was 4x to the third. The difference used to be that there was just an x here. But remember, the x stayed the same. We never did anything to the x. So the base stays the same. You don't do anything with that at first. But the derivative, if you just had x, the derivative of x equals 1, because you would do 1 times 1 is 1, and then you would rewrite the base, and then you would decrease the exponent by 1 to a 0. 1 to the 0, or x to the 0 is 1, so that equals 1. The derivative of x is 1. It's a linear piece that has a slope of 1. So in all the power rules and even product and quotient rules we learned already, there was always just an x for a base on any given exponent. They never had a bunch of stuff raised to an exponent until this point. If the base is just x, the derivative of x is 1, and then you're in essence getting a 1 for that it's going to get multiplied here on, but when you multiply by 1, it doesn't matter. So the chain rule is basically, if this stuff is something different than just x and its derivative isn't just 1, then it matters, and you have to chain it on. You multiply it onto the back, and that's why it's called the chain rule. It's like you attach it to the end of the answer you would have gotten. So the only thing new here, there's not really anything new in terms of derivative rules. I'm doing the power rule first, 4 base to the third power, and then I'm going to multiply by the derivative of the inside. And you can go back now to section 4.1 and 4.2 and still do this every time. If you were back in section 4.1 and you had 4x to the third as a problem, x to the fourth as a problem. If they gave you y equals x to the fourth in section 4.1, and you told them the derivative is 4x to the third, then you can now chain on the derivative of the base. But the derivative of x is 1, so it doesn't affect anything. So they didn't waste time teaching you this in the first 2 sections because it was always a 1 and didn't matter yet. So now I guess they waited till you learned a few more derivative rules so that you can handle a few more things while you learn this rule too. So I need to tack on, let me write this a little better, dy over dx. You're kind of doing the outside part first, 4 times the base raised to the third power, and then times, and I was trying to write this better so there was room, but now you do times the derivative of the inside, and that's just doing power rule over and over again itself. That's not hard. So I'm just going to pretend that this parenthesis is attached here in the back. Do the power rule on the inside part now. 4 times 3 is 12, x to the third, minus 8. This is what we did in 4.1. X to the first, and the derivative of 8 is 0, so that's it. Okay, so then in terms of cleaning this up a little, you can definitely put a constant in the front of the answer. Typically, if you have a parenthesis with a power and another parenthesis that doesn't have a power or just has a 1, then they'll typically put that part next. 12x to the third minus 8x. And then I can do this part that had a third power. The original problem was in there. 3x to the fourth minus 4x squared plus 8. When a parenthesis part has an exponent different than 1, then you're never going to be able to do anything with this. That's going to definitely be in the answer. A couple of things you could do with this. Since it's first power, you could distribute the 4 back in if you want. and get 48x to the third minus 32x times this. Or you could say, well, what I pulled the 4 out already. Why don't I get a GCF and go the other way? 12 and 8 both divide by 4, and they both have an x. So this parenthesis part alone has a 4x GCF. And that would leave you a 3x squared minus 2 left over. And then you could multiply the 4 to the 4x and get 16x. 3x squared minus 2, which that part has no more way to factor it. And then finally the 3x to the fourth minus 4x squared plus 8 to the third power. So here we go again, where all of these are equivalent. And in general, it doesn't matter which one you do. We can check in MyMathLab. They would probably just take this version of it. I think that directions are generic enough. Well, I'm not even on the right problem here. Let me go back here. Here it is. Okay. See, it just says find the derivative. Type an expression using x. It says nothing about factoring or distributing. Any of those answers should be good. And you can waste time doing extra things, but then you always take the chance of making some kind of brain cramp mistake like I did on the last section. So why distribute if you don't have to? Why factor if you don't have to? But if somebody did one of these other two, they are equivalent. And this is the issue we used to have back in the day when we'd look up answers in the back of the book. Sometimes they would just leave it like this. Sometimes they would distribute. Sometimes they would factor. They would just kind of do it willy-nilly every so often, just do it different ways in different problems just to mix it up and show that anything was possible. But the problem was students would get one version and not know if theirs was equal to the one that was in the back of the book. So now the nice thing is you can, in homework at least, until you learn what they want before you take a test, you can just put in a particular answer you have. And because the directions are so generic, they should accept this answer. 4 times 12x to the third minus 8x. And then I have my original base, 3x to the fourth minus 4x squared plus 8. And then the exponent got decreased to a 3. So they took this, but they would definitely take the distributed version. There's nothing wrong with doing that. There's nothing wrong with pulling out a GCF. So it just depends on your preference in the final analysis. But at least they take this version, so then you don't have to waste time doing those other algebra steps. Okay, so similar deal here on number 3. I have a k of x, and they want me to find k prime of x. So that's clear notation to find a derivative. K of x, and then find k prime of x. That tells you to do the derivative. And this time we have a negative 3 times 8x squared plus 7 to the negative 6 power. So you can't distribute this negative 3 because there's an exponent here that's not a 1. If there's any exponent here other than a 1, you definitely can't distribute or factor to pull any GCFs out. I can use the power rule though and do exponent times the constant. Negative 6 times negative 3 is positive 18. The base would stay the same. And then I would decrease the exponent by 1. Negative 6 minus 1 is negative 7. But the base wasn't just x. If the base had just been x, if I just had negative 3x to the negative 6, then I would be done at that point, because the derivative of x is 1. But the derivative of this is not 1. So that's the best way to tell, is you always keep the base the same. And then just ask yourself, what's the derivative of that base? If you say 1, then there's nothing to chain on. But if the derivative of that base is different than 1, then you got to chain on that derivative answer. So what if I had this as a whole problem, 8x squared plus 7, what's the derivative of that? See, this is the inner function. And that's just an easy power rule. 8 times 2, 16, x to the first, and the derivative of 7 is nothing. So it was a simple derivative, but it needs to be chained down. If you don't put that part attached to the answer, then it's going to be wrong. Now, maybe they would take this answer, but to me, it's simple enough just to do 18 times 16. Why not make that look a little better? 18 times 16 is 288. So it would just look a little better if I wrote 288x. I'm putting that part in the front. Any parenthesis to an exponent, that usually goes in the back of the answer. So 288x times this quantity to the negative 7th power. And then you could also do, see, here's another thing. You could then say, well, I don't like negative exponents in my answer, so I'm going to put it down in the bottom. This is not wrong to do that. It's just another possible answer. These two are equivalent to each other. It doesn't matter which one you do. You could make a brain cramp mistake in the process of doing the second one, so why do that if you don't have to? I wanted to mention one more thing. Okay, well, I can't think of it. Okay, so I would just do 288x and then keep your 8x squared plus 7 base. And then that got raised to the negative 7th power. Oh, that's what I was going to say. Okay, so when you have an answer, at least on a test, one possible way to make sure you did this right is, well, I guess I'm getting ahead of myself, actually. That's going to be true later, so we can't really do that here, but you got to learn another chapter before you can do that. Okay, so forget that, scratch that idea. Okay, so now I have an 8 times a square root of 8t squared plus 9. And they call it f of t, and then they want f prime of t for the answer. So f of t is 8 square root of 8t squared plus 9. So we generally like negative exponents. They're easier to work with in derivatives than putting them 1 over. And another thing that's easier to work with is fractional exponents instead of radicals. Even though most people don't like fractions, but I would change this square root. Remember, square roots are the same thing as 1/2 powers. So if you do this first, now you've got a power rule with a chain rule attached. So the derivative of f of t is f prime of t. Do the power rule first. Exponent times constant. 8 times 1/2 is 4. Then you rewrite the base, which normally it used just to be a t, but now it's more stuff than just a t. And then you decrease the exponent by 1. 1/2 minus 1 is negative 1/2. And then times, if the base has a derivative of anything other than 1, then I need to attach something onto it. And the derivative of this base is different than 1. The derivative of this right here is 16t to the first. 16t to the first. The derivative of 9 is nothing, so then just 16t. And then we could easily combine 16 times 4 and get 64t times this to the negative 1/2. And that would be the least amount of work to get the answer right. But then you could say, well, I don't like negative exponents, so I'm going to put it in the bottom. 8t squared plus 9 to the positive 1/2. That's an equivalent answer. Or you could say, well, the original problem was a radical, and I just changed it to a 1/2 temporarily. What if I put it back as a radical? That's another equivalent answer. So any of these three would definitely be acceptable. But again, you're just wasting time and doing stuff that might cause a brain cramp type mistake where you leave something off accidentally. You could easily forget to write this square in your process of doing that, or other little mistakes that we all make. So 64t. And then I would just leave it in the parenthesis 8t squared plus 9, and then that'll be raised to the negative 1/2 power. Okay, so now we're going to start mixing rules together. Here's a function of x, 4x plus 3 to the 5th power. Here's a function of x, 5x plus 1 to the negative 2, and they're literally multiplied together. A function of x times a function of x, that's the power rule. And in the middle of this power rule, you're going to have chain rules going on. Y equals 4x plus 3 to the 5th. Times 5x minus 1 to the negative 2. So here's my first function of x. Here's my second function of x. Remember the product rule? First times derivative of the second plus the second times the derivative of the first. So my first function, you just rewrite it exactly like it looks. Second function, I'm going to do the power rule and do negative 2 times 1, which is negative 2. Rewrite the base. Decrease the exponent by 1. Negative 2 minus 1 is negative 3, but then chain rule. The base, I rewrote it at first, but if the derivative of it is anything but 1, we need to chain it on. The derivative of 5x minus 1 is 5 because that's a linear mx plus b format. So the derivative of that's 5. Plus, now you do the second function exactly like it is. And then times the derivative of the first, but the derivative of the first is going to be at first a power rule and then a chain rule. 5 times 1 is 5. Rewrite the base. Decrease the exponent by 1. And then derivative of the inside, that's 4. So again, with 4x plus 3 here to the 5th power, you can't really do it. You can't pull anything out or distribute anything in. I could combine these two numbers together. And this is all multiplied here. So up till the plus part, I can put the negative 10 way out front. And then I got both of these parentheses in whatever order you want because they both have exponents attached to them. Again, possibly you could drop this to the bottom and make it positive 3, but that definitely wouldn't help here. 5 times 4, 20. I would put that in front. And then I've got a, again, order doesn't really matter, but I'll put this one first. And this one second. So again, this is probably acceptable for the answer. There is a GCF though, all three parts. Both 10 and 20 divide by 10. So somebody could say, I'm going to do a GCF and pull out 10, or even negative 10 if you want. Both terms have 4x plus 3, so then you take the one with the smaller exponent. 4x plus 3 to the fourth power. And then they both have a 5x minus 1. And you always do the smaller exponent. Negative 3 is actually smaller than negative 2. So I took the 10 out, but not the negative. I took 4x plus 3 to the fourth, but there was 5 of them here, so there's an extra 4x plus 3 right there. But I took this one entirely out. Plus 20 divided by 10 is 2. I took the 4x plus 3 entirely out, and then I took all but 1 of the 5x minus 1s. And then potentially you could do this and put all that together. There's going to be a 10x here. There's a negative 4x there. That's 6x. And then there's a negative 2 and a negative 3. That would make negative 5. So that would be another factor you could put instead. So then the final answer of this version could be 10. And then you'd probably put that 6x minus 5 first, just because it doesn't have an exponent. Then put these two. So you could have 4 factors: 10, 6x minus 5, 4x plus 3 to the fourth, and 5x minus 1 to the negative 3. But that took a while to do all that, and there was some messy algebra involved, and factoring is hard. If they'll take this answer, then why do all that work? So let's try that first. Negative 10, it just says find the derivative, very generic. So as long as you find the derivative at one point of it, they usually take that answer. Negative 10, 4x plus 3 to the fifth. And then there was a 5x plus 1 to the negative 3. Plus 20, the 4x plus 3 here had a fourth power, and the 5x plus 1, this one had the negative 2, I believe. Let's check that. 24 negative 2, 4 negative 2, yeah. See, they took all that, so all that distributing and GCFs that could be done, and it wouldn't be wrong to say the answer is down here. You could say this is the answer if you put all this together. So you'd have to have the 10, you'd have to have the 6x minus 5, you'd have to have the 4x plus 3 to the fourth, and the 5x plus 1 to the negative 3. If you had all 4 of those multiplied together, that would be an equivalent answer. And it looks nicer than this big mess right here, is the advantage of it. Maybe you remember in algebra how we sometimes have the polynomial form, and then we have the factored form, and each one has positives and negatives. Like the factored form helps you to see the zeros of the function easily, but the polynomial form, you can see the end behavior. So similar kind of deal. Maybe somebody likes this big longer mess because it was easier to do. Other people might like the cleaner factored version. So we just did a product rule. Now hopefully you recognize this as a quotient rule. I've got a function of t divided by a function of t. So f of t, the numerator is 5t minus 3 cubed. And the denominator 7t squared plus 2. So derivative of a quotient, remember how it goes: second times derivative of the first minus the first times derivative of the second over the second squared. It has 3 differences from the product rule. Product rule's got the first, and the quotient rule has the second first. Product rule's got the plus in it. Right here, plus. Here's first is first, and it's plus. Here is second first, and a minus. And then the quotient rule has this extra divided by part that the product rule doesn't even have a divided by part. Okay, so do your second function exactly like it is. 7t squared plus 2. Then times the derivative of the first, but the derivative of the first is a chain rule. Product rule, it's a power rule with a chain rule. 3 times 1 is 3. Rewrite the base. Decrease the exponent by 1, and then multiply by the derivative of the base, which happens to be a 5, since that's a linear piece. So that's first times derivative of the second minus, I said it wrong, second times derivative of the first minus first, so just write that one, times the derivative of the second. Now this one, see, watch what happens here. So this is a polynomial. There's no parenthesis and an exponent attached to it. So I would just go term by term. This is just like section 4.1 right here. The derivative of this term is 14t to the first. And the derivative of 2 is nothing. And there's no chain rule here. Technically, it's times 1 because the base is t. It's not a quantity like that. The only base here is t, and the derivative of t is 1, since that's just a linear part. So that bottom here is not a chain rule, other than saying that you're chaining on a 1. And then divide by the second squared. Okay, so probably again we can just do the 3 times 5, 15. And then I would put the 7t squared plus 2 part first, right here. And then put this squared part next. 5t minus 3 squared. And then here, after the minus, put the 14t first. And then the 5t minus 3 cubed. All over the second squared. And yes, there's a GCF of 5t minus 3. You could pull that out, but that would be the only GCF. The 14t doesn't have anything in common with these two. Or you could distribute this 15 in here if you want. But if they take this answer, why do any of that extra stuff? So here is the quotient rule answer with a chain rule mixed in at this part only. There was no, pointing at the wrong spot, right here was the one chain rule. There was no chain rule other than 1 right there. So let's try this. 15. Oops. 15. And then there was the 7t squared plus 2. Was that the next part I had? Yeah, 7t squared plus 2. And that's first power. And then the 5t minus 3 was squared. 5t minus 3 is next. Squared. Minus. Then I slid the 14t into the front of this part. So that way the back would have the exponent. It's always nice to have the back and the back. Put the exponent in the back, like here, instead of the 14t in the back, because then the exponent's a little more noticeable. 5t minus 3 raised to the third power. So you have the 15, you got a parenthesis that has a first power, and then you got a parenthesis with a second power. And then I just got a 14t and then a parenthesis with a third power. Putting those exponents in the back of each part just helps make them stand out a little better. And then the original denominator is squared as usual for the quotient. Remember how you squared the bottom, and it usually doesn't change all the way to the answer. Only if you could factor the top and cancel that out, but the only common factor in the top are the 5t minus 3's. And they don't help me cancel this denominator, so then that's when you don't have to factor it. Okay, so now we're going to take another application here that we've done before. Find the equation of the tangent line. That always comes back anytime you're working with derivatives. Find the equation of a tangent line to the graph of the given function at the given value of x. So my original function is f of x equals square root of x squared plus 11. I want to do it at x equals 5. Find the equation of the tangent line. That's code for do the derivative. F of x equals the square root x squared plus 11. X equals 5 is the place we want the tangent line to be. So if I do the derivative of the function, since I'm looking for a tangent line, the derivative of that spot will be the slope of the tangent line. But I should rewrite this original function not as a radical, but as a fractional exponent. That's a 1/2 power. So I'm going to do the derivative of this with the power rule. 1/2 times 1 is 1/2. Rewrite the base. And then decrease the exponent by 1. But then times the derivative of the inside if this base has a derivative different than 1, and it does. The derivative of x squared is 2x. And the derivative of 11 is nothing. But there's the chain rule coming into play again. And then this 2 could cancel that 2 because neither one is part of any exponent. So all I have left is x. And I am going to this time, and this is why it does matter. Sometimes I'm going to first put this parenthesis in the denominator so that the negative 1/2 can turn into a positive 1/2. And then I'm going to change it back to a radical. Remember a couple of problems ago, I showed you that you could do this, but said it didn't need to be done. So if they just asked me what the derivative is, I would just probably leave this as the answer. But what's different here is I need to plug 5 in a second. I need to know what's f prime of 5 because that'll be the slope of the tangent line at 5. And it's hard to plug a 5 in when there's a negative exponent or a fractional exponent. So I got rid of the negative exponent, then I put it back as a radical. Now it's easy to plug 5 here and there. So that's why, even though before we didn't have to do it, it's always good to know how to do it because sometimes it's more convenient to do these other methods. So square root of 5 squared is 25 plus 11. That's square root of 36. Square root of 36 is 6. So the derivative at 5 is 5 over 6. That's the slope of the tangent line. So we know half the answer right now. Half of the answer is y equals 5 over 6x plus b. But we don't know the b, the y-intercept. And they only told me an x. They didn't tell me the y. So I can plug 5 in down here, but I don't have a y at the moment. So whenever you're missing the y, you always plug that into the original function, not the derivative. Plugging 5 into the original function, f of 5, remember that f of x is the same thing as y. So f of 5 says when x is 5, here's what y is equal to. So 5 squared plus 11, and that's the same as the denominator here, so that's going to equal 6 eventually. But the y is exactly 6. It's not 5 over 6, it's just 6. Put 6 in here, and put 5 right there, and solve for b. So you'd have 6 equals 5 over 6 times 5 plus b. So this is going to be messy, but 5 times 5 is 25. So I'm going to subtract 25 over 6 to get b by itself. And the issue is that 6 has a 1 in its denominator. They need to have common denominators, otherwise you can't subtract them. So you'd have to multiply this by 6 over 6, and that would turn it into 36 over 6 minus 25 over 6. That's 11 over 6. This is what b equals. So the final answer, the equation of the tangent line is y equals 5 over 6x plus 11 over 6. So the tangent line would be going up 5 over 6 over and over again, and it would cross the y-axis at just a little less than 2, 11 divided by 6, at exactly that one spot on the original function. So y equals, they already have the y equals, we'll look for that because sometimes they don't put it, 5 over 6x plus 11 over 6. Oops. So we've done that a number of times. Once we learn new derivative rules, they always bring this back out again. And here's another one we did in the past too. Find all x values of x for which the given function where the tangent line is horizontal. If a tangent line is horizontal, that means the slope is 0. And so tangent line slope is derivative. So I want to find the derivative of this function and then figure out when it's equal to 0. So the original function is a big messy square root x cubed minus 12x squared plus 45x plus 1. So if I want anything to do with tangent lines, we're definitely doing derivatives. And think of this as to the 1/2 power. It's like this square root is a 1/2 power. And then you can do the power rule. 1/2 times 1 is 1/2. Rewrite the base. Then decrease the exponent by 1. 1/2 minus 1 is negative 1/2. And now chain rule. The derivative of the base is definitely not equal to 1. The derivative of this 1 in the back is 0, but all the rest will have something other than 1. The derivative of x to the third is 3x squared. 3 times 1, and then decrease the exponent by 1. The derivative of this will be negative 24x to the first. And the derivative of 45x is just 45. So you might want to clean this up if we're going to be setting equal to 0. So 1/2, the 2 can go in the bottom. The 1 would be in the top if there was nothing else there, but if there's other stuff there, then it won't be there anymore. So all of this is going to stay in the top. And then you could move this negative 1/2 to the bottom, make it positive 1/2, but then you could make it a radical after that. So there comes the radical back from the original problem. So this would be the derivative, and I wouldn't necessarily have to write it this way. I could have left it, if they just said find the derivative, I could have left it like this and maybe just rearrange the order of it. But since I'm going to be working with it, I want to work with it in an easier format than having a negative 1/2 power, which is hard to work with if you're going to do calculations. So we want the tangent line to be horizontal. A tangent line is horizontal when the slope of it, which is the derivative, when the derivative is 0. If a derivative is 0, then the slope of a tangent line is horizontal. And so that means the answer has to equal 0. A fraction only equals 0 when the top is 0 and the bottom isn't. So then I could first solve for what x's make the top of the fraction equal 0. And because it's squared, there's going to be 2 of them potentially, unless it's the same number twice. And luckily all these numbers divide by 3. So then I can get not only a nice 1x squared, but I can get smaller numbers too. And 0 divided by anything is 0, so it doesn't even hurt that side. So the 3's cancel, you get x squared. 24 divided by 3 is 8. 45 divided by 3 is 15, and let's hope this factors. So we want two numbers that multiply to 15, and then they would have to add to negative 8. So if the last sign is positive in a trinomial, then in your answer you get 2 of the front sign. I'm going to definitely get 2 negatives here. The most common way to multiply to 15 is 5 and 3. And luckily, negative 5 and negative 3 does make negative 8. So there's two x answers that make the numerators 0, 5 and 3. Then we would just want to make sure they don't also make the bottom equal 0, which wouldn't be so easy to tell. But we could use some technology here to tell. So just a quick double check, because if you have 0 divided by 0, that doesn't equal 0. But if I have 0 divided by anything else, then it would equal 0. So I'm going to plug 5 into all of these x's here. I need to make sure this square root doesn't equal 0 when x is 5 or 3. Otherwise, I have to cross that answer out. So 5 to the third power minus 12 times 5 squared plus 45 times 5 plus 1. This better not equal 0, otherwise we got to cross this 5 out. I don't know if you can see that or not, but there. It equaled 51, so that's okay. So 5, if I plug 5 into the entire fraction, the top will be 0, but the bottom won't be. I don't care that it's messy, but 0 divided by anything other than 0 is equal to 0. So as long as this 5 doesn't make this 0, then we're good. Same thing with the 3. Now, since I already typed it with a 5, a quick way to get the other one is hit second enter, which calls up the last statement you typed in. And then you can just back up with the arrow keys on top of the 5s and put 3s for each one. And that way you don't have to retype the whole thing. So now I have 3 to the third minus 12 times 3 squared plus 45 times 3 plus 1, and that equals 55. So neither one of them made 0 at least. So then both of these are spots on the original graph. It would be hard to know what that original graph looks like too, but these would be two spots on the original graph that the tangent lines touching those spots would be horizontal because they make the derivative equal 0. And a fraction equals 0 if the top is 0 when the bottom isn't. So two x answers, 3 and 5, or 5 and 3. I don't think order matters, but 3 and 5. Okay, so then we'll get a couple of application problems. We've got test individuals' use of certain mineral. Okay, they inject a small amount of radioactive form of that mineral in their blood. The mineral remaining in the bloodstream is measured each day. So suppose that you have the amount of mineral remaining in the bloodstream in milligrams per cubic centimeter T days after the injection is approximated by this function, which looks eerily similar to a lot of the ones we've already had in this section. Find and interpret the rate of change. Rate of change, that's derivative. Slope of a tangent line or rate of change. Those are two key phrases to say find the derivative. And then we're going to do it for 0 days, 3 days, 7.5 days. Okay. So clearly the first thing we need to do is get a derivative, and probably the chain rule is going to come into play because this problem's in the chain rule section. So my C of t is 1/2, and then times a base of 2t plus 1. Notice the base isn't just t, it's more stuff than that, so that's when the chain rule matters. 2t plus 1 raised to the negative 1/2. So rate of change, that's derivative. Power rule first, negative 1/2. times positive 1/2 is negative 1/4. Rewrite the base. Decrease the exponent by 1. Negative 1/2 minus 1 is the same thing as negative 1/2 minus 2/2. That's negative 3/2. We are going to be plugging numbers into this, so I would put the negative exponent in the bottom, maybe even use a radical here. So we got a negative 1/4. And now we're going to have to put the 1 in the top because nothing's going to remain in the top. So first you would get a 2t plus 1 to the 3/2 by putting it to the bottom. And then you could make this negative 1/4. And you could do a square root. The denominator 2 is a square root. And then there'd be a 2t plus 1 to the 3rd power inside the square root. So this is some algebra simplification, because the only reason why, if they just said find the derivative, I would stop right here. But they want me to plug in 3 numbers starting with 0 first. So part A is find the rate of change for a time of 0 days. So in other words, t equals 0, but you got to plug it into your rate of change derivative function. It's hard to plug it in here or here because you got these negative and or fractional exponents. But plug it into the radical might be easier now. So if you put 0 in right there, 2 times 0 is 0, plus 1 is 1, 1 to the 3rd power is 1, and the square root of 1 is 1. So that came out nice. This part equals 1. So the answer is just negative 1/4, literally. Or if you want a decimal, negative 0.25. Round to 2 decimal places, so they didn't want the fraction. The rate of change for the mineral with respect to time for 0 days is blank milligrams per cubic centimeter per day. Milligrams per cubic centimeter. So yeah, looks like that's it. Sometimes you got to worry about the units changing in the answer compared to what we started with. Okay, maybe that is what's going on. Milligrams cubic centimeter, huh? Okay. I plugged in 0. 3/2 square root, definitely. 2t plus 1 is 1. Negative 0.25. Oh, I know what I did wrong. I forgot the chain rule. So yeah, right here. I said it before I started the problem and I didn't do it. So the derivative of the inside, we forgot that. I forgot that. 2t plus 1 is a derivative of 2. So without that, it's wrong. So there is a 2 in the top, not a 1. So it's negative 2/4, which is negative 0.5. Not negative 0.25, but negative 0.5. So there we go. Now do it for 3 days. Oh no, wait, they want an interpretation first. So at 0 days, which is what I plugged in, the bloodstream is, remember, if it's negative, you're decreasing. It's decreasing by 0.5 milligrams per day. You don't say decreasing by negative 0.5 because that's a double negative. So decreasing, I got negative 0.5. The negative is the decreasing, and the 0.5 is what it's doing per day. Okay, so now plug 3 in. So now what I'm doing is, let me rewrite my derivative correctly this time. Forgot the chain rule. It should be right here. Well, actually, I want this one. Negative 2/4, and you could even reduce that to 1/2 now. So negative 1/2, not over 4. square root of 2t plus 1 cubed. And this time we're plugging in 3 instead of 0. Okay, so 2 times 3 is 6. 6 plus 1 is 7 to the third power. So this one's not going to come out nicely. Let me do this where you can see it better. This one's simple enough to do here. So 7 raised to the third is 343. Then I need the square root of that times 2. And then it's negative 1 divided by this. So if you do 1 over, that's how you can get 1 over and just make it negative. They said round to 2 decimals, so negative 0.026 would be negative 0.03. Negative 0.3. This was definitely calculator because it didn't come out nicely. This one came out nicely because I got the square root of 1 right here. But now I'm getting the square root of 343, which doesn't come out exactly. Negative 0.03. That's the derivative. And that means it's decreasing by 0.03. After 3 days, it's decreasing by 0.03. But you don't put negative 0.03 there. This one's negative 0.03, but the negative tells you the decreasing, and then you just put 0.03 there. And then finally, part C, 7.5. So now I need to put a 7.5 right here. 2 times 7.5 is 15. Plus 1 is 16. Well, that's nice. Oh, no, wait. Okay. I was thinking square root of 16, but it still should come out nice. Square root of 16 is 4, and then you could do 4 to the third. Or you can do this to the third and take the square root of it, and you get the same answer. The square root of 16 is 4. 4 to the third is 64, and this is 64. And then you still have your negative 1/2 there. So C prime of 7.5 is negative 1 over 2 times 64, which is negative 1 over 128. So 1 negative divided by 128. Negative point, James Bond 007. And we're going to round to 2 decimals, so negative 0.01. So that one will be decreasing by 0.01. The answer is negative 0.01, but then it's decreasing by 0.01 after 7.5 days. Decreasing by 0.01. Okay, what does D say? Are the slopes of the tangent line always positive or always negative? Well, they're all negative here. My 3 derivatives were negative 0.01, negative 0.03, and negative 0.5. And not only were they all negative, they were getting closer and closer to 0, actually. So they were kind of getting closer and closer to horizontal. So it went from a little steeper to less steep to almost horizontal. But they're always negative. And the slopes of the tangent line are always negative, so are the rates of change, because slopes of tangent line and rates of change are the same thing. So slopes of the tangent lines are always negative. The rate of change is always negative. Although it's starting to get close to no change if you could get to 0. But you'll never reach 0 because there's a 1 in the numerator. But it gets closer and closer to it. Okay, this is weird. Zen z cube. A zen z cube is an obsolete word that represents the square of a cube. In symbols, zen z cube is written x to the third to the second to the second. Use the chain rule twice to find the derivative. use the properties of exponents to first simplify it and then find the derivative. Well, that part's actually easier. Let's do that first so you see what's going on here. So I've never heard of a Zen-Z cube, but we all learn something new every day. So x to the third squared and squared. The rule of exponents when you have one base and exponents to exponents is you multiply them. The base stays the same. You do 3 times 2, 6, and 6 times 2 is 12. So part B said use the rules of exponents to simplify it first. And now to do the derivative of this, that's very easy. The derivative of this is 12x to the 11th. Because you do 12 times 1 and decrease the exponent by 1. So I did the easier part first because then I know what the answer has to be. It has to be 12x to the 11th. Now they want me to do the chain rule twice. Remember, chain rule, you do the outermost part first. And you're just going to do a power rule. 2 times 1 is 2. Rewrite your funky base. Don't change the inside. You do 2 times 1 times whatever the inside is. Remember, the bases never change in derivatives. And then decrease the exponent by 1. Now we need to chain on the derivative of the inside. So the derivative, if this was my whole problem, now I do it again. So now do 2 times 1 is 2. Keep the base the same and decrease that exponent by 1. But wait, there's more, like in those late night infomercials, and this is why they said use the chain rule twice. Now I got to do the derivative of this inside one. Although that's just a power rule, that's just 3x squared. Okay, so these outer ones aren't going to matter. I've got 2 times 2 times 3. What do you know? That's 12. X squared times x to the third. Notice that's 2 different x's. That's not the same as this right there. One base with multiple exponents, you multiply the exponents. If they each have their own base, then you add the exponents. And this one's only got one base, so that's when you multiply the exponents. And notice x to the 6th times x to the 5th is x to the 11th. That worked. So I did the outer derivative first, then I did a chain rule, then I did a chain rule. The chain rule can happen multiple times, actually. So then you just keep tacking it on to the end. And then simplifying this big mess, it equaled the answer, 12x to the 11th. Okay, so whenever you have one of these functions inside a functions deal, f of g of h of x. So you're doing the derivative of the outer part first. We did the outer part first. So you do f prime first. Notice every answer's got f prime first. But you wouldn't touch the inside at all. You would leave that entirely as it is. So it'd be f prime times the inside just like it looks. Like this D answer or this A answer. F prime of g of h of x. Then you go to the next outer one, which is g. So g prime is next. Of the inside stuff, h of x. They both have that. But remember it said use the chain rule twice. So that's why the answer is D. Then you also have to do the derivative of the innermost one, which is h prime of x. So that's a chain rule right there in symbols, where you just keep doing the next inner one after the outer ones. Okay, now determine expressions for u, n, and y. What is the expression for u? U is h of x, and that's the innermost one, so that would be the x to the third. Okay, so that should be u. Then the g part is the middle one. So you don't write this, you just say, remember how you plug this in for that one? So it's literally just put an x for this and squared. X squared is the format of it. Whoops. Okay, so do they want it that way? Okay, I was thinking that we would take this and just put it in for that x, but maybe they want it written the way it looks. So let's do x to the third. I guess they're plugging it in already. They're plugging in the x to the third for that spot, and then that gets squared. Nope, okay. Expression that represents g of u. G is the squared part of the h of x. H of x, g of h of x. Oh, I know why. Maybe it's this. And delete this, delete. There. Since it's g of u, maybe they just want u instead of x. That's what I think I did wrong. Is it should just be, remember I had x squared here at first? So they do it with a different letter. Okay, so g of u, that means you have to use the letter u. But my first thought was right, that you just want x squared here or u squared, because then this is going to go in place of it. You're going to stick that x to the third in for the u. So now find f of n. So that's the outer one. So again, there's something squared, but you have to use the letter they're giving you. So that one's n squared. So h prime of x, the derivative of x to the third is 3x squared. The derivative of g of u, just look at your g of u, the derivative of that would be 2u. And the derivative of f of n, fn is n squared, so the derivative of that would be 2n. So, okay, so what is the result? That should be our answer of 12x to the 11th. And we did it two different ways and confirmed it was the same answer both ways. And this is the same answer this way too, as it should be. Okay, I didn't read it, sorry. It wants me to do the rules of exponents first. Use the properties of exponents to simplify. That's when you multiply the exponents. So they didn't want the derivative yet. They want the function simplified, the original function. So using properties of exponents, this simplifies the x to the 12th, and then they'll probably have me do the derivative of it. Yeah, see, there's the derivative. I was jumping ahead too far. 12x to the 11th. Okay, so not so bad this time. 100%, 10 out of 10 for section 4.3. That's called the chain rule. And where's our assignments? So we've done 3-3, 3-4, 4-1, 4-2, 4-3. We got 5 down, 2 to go. Derivatives of exponentials will be another video this week, and then next week, derivatives of logs, followed by the review. So that's it for section 4.3, the chain rule.